It's my pleasure to start the first meeting, joint meeting of St. Petersburg Mathematical Society and Cohomology program in the Euler Institute. And our first speaker is Professor John Morgan from the Simons Center of Geometry and Physics, Stony Brook University. And John Morgan is a famous expert in topology and geometry, and he is well known for his work with Gang Tian on geometrization program. And so he'll speak about topology of manifolds, please.
Thanks, Leon. I wonder what Leon really said about me. It's a great pleasure to be here. I have many mathematical friends who started out life here in St. Petersburg, so it's a great pleasure to come and see where they started life. This is my first trip to Russia, my first trip to St. Petersburg. So it's a great pleasure to be here. As Leon said, I have a math institute in Stony Brook in New York, and we have a very nice building, I think, but we have no room that compares with this one. So this is quite an honor to be able to talk in a room like this. So I've decided to give you today a survey of, how long has it been? 50 years, 60 years of progress studying the topology of manifolds. And I'll divide my talk into three parts. Well, I'll start with a general introduction about various manifolds, various types of manifolds, and in general how the various types are related. But then the first real topic will be high-dimensional manifolds, which means manifolds of dimension 5 and higher. And I'll talk a little bit about some of the very classic work that dates from the 1950s and 1960s about those manifolds. And then after that, we'll concentrate on the exceptional and much more complicated low dimensions, 3 and 4. And I'll give you a survey of the current state of affairs in 4-dimensional topology. And then after the break, I'll talk about 3-dimensional manifolds. Though I must admit, especially when I get to 3-dimensional manifolds and I talk about Alexandrov spaces and Gromov-Hausdorff convergence and Perlman's work on applying Ricci flow to the study of 3 manifolds, I feel very much, as the old English expression goes, that I'm bringing coals to Newcastle. I'm bringing back to you what you already have, or what came from here originally. All right. So, as we know, all manifolds have local coordinates which look like the coordinates in an open set in some Euclidean space. But you can have different types of manifolds depending on the consistency conditions or overlap conditions on these manifolds. And we're going to talk about 3 different types. Topological manifolds, where you make no assumption at all except the overlap is bicontinuous, so it's a homeomorphism. Smooth manifolds, where the overlap functions are required to be infinitely differentiable. And piecewise linear or triangulated manifolds, where the overlap functions are simplicial on some rectilinear subdivision of the pieces of Euclidean space. Maybe I should say back on smooth manifolds, I required in my brief introduction that the overlap functions be C infinity, infinitely differentiable. You could require them to be C1, C2, C2 in some Sobolev space. There's many different classes of manifolds you could imagine, but in fact it turns out that once you have C1, C1 manifolds are equivalent to smooth manifolds. So every C1 manifold has a smooth structure inside the C1 structure, and any 2 are smoothly isomorphic. So one can concentrate just on C infinity. All right, so those are the 3 classes of manifolds. As we go through the various dimensions, we will see differences, analogies, sometimes equivalences between these categories of manifolds. But in general, there are a few things we can say. Any smooth manifold is clearly a topological manifold, and any piecewise linear, PL manifold, is obviously a topological manifold. Also, a smooth manifold can be triangulated or given a piecewise linear structure. A quick proof of that. Embed the manifold smoothly in Euclidean space. Triangulate some neighborhood of the manifold very, very finely and in general position with respect to the manifold. And then intersect the manifold with the pieces of the triangulation, and this will give you a cell structure on the manifold, a linear cell structure, and you can subdivide that to get a triangulation. So in general, we have smooth manifolds give us piecewise linear manifolds, and piecewise linear manifolds give us topological manifolds. Now, for low-dimensional manifolds, surfaces and three manifolds, in fact, these categories are completely equivalent. Every topological manifold can be triangulated, and every piecewise linear manifold, dimensions 2 and 3, can be given a smooth structure. Actually, triangulating topological, even topological surfaces is a non-trivial theorem. Triangulating topological three manifolds is quite a deep and complicated result, but was known early on.
Just in dimension 4 smooth is bit, or?
Yes, we're coming to that.
But you say that it is not.
In general, you can't reverse these arrows. Cannot.
In dimension 4?
No. In dimension 4, it's smooth and PL are the same. You're getting ahead of the story here. Okay, high-dimensional manifolds. So as I say, high means dimension greater than or equal to 5. And it turns out there's a very general, robust understanding of these manifolds. And you start usually with the underlying homotopy type of the manifold. So the homotopy theory of the manifold. And you try to understand all the topological, piecewise linear, or smooth manifolds in a given homotopy type. So I've just picked out a couple of simple sample conjectures. I'm not going to try to give you the entire theory, but one is the generalized Poincare conjecture. Suppose you have a closed either topological or piecewise linear manifold, which is the same homotopy type as the n-sphere. So there's a map from it to the n-sphere and a map back so that both compositions are homotopic to the identity. Then, in fact, the manifold is homeomorphic or piecewise linearly equivalent to the sphere. So this is a theorem that says there aren't any interesting manifolds of this homotopy type. And this was proved, well, the topological version was proved by Smale in 1961, piecewise linear version by Stallings quickly thereafter. Now, that was a theorem in the topological and piecewise linear category. There's a very different theorem for smooth manifolds. So let's look at smooth manifolds, homotopy equivalent to the n-sphere. Turns out they form a finite abelian group under connected sum. If you have two manifolds of a given dimension, you can take little balls out of each one of them and connect them together. You can do that smoothly if the manifolds you're dealing with are smooth. That's called connected sum. And if you take two manifolds homotopy equivalent to the n-sphere and you do this operation, you get another manifold homotopy equivalent to the n-sphere. And it turns out for smooth manifolds homotopy equivalent to the n-sphere, under this operation, they make a finite abelian group. And in principle, at least, you can compute this group. One of the first ones that was computed was a group in dimension 7, where it's a cyclic group of order 28. Denominators of Bernoulli numbers come in as you do higher dimensional homotopy spheres in dimension 4k minus 1. This is not known in dimension 4. It's not known whether they're finitely many or infinitely many different four-dimensional manifolds, smooth manifolds homotopy equivalent to the 4 sphere. So this is definitely a theorem in dimensions 5 and higher. Oops. Okay. Now let me give you a general result relating the relationship, well, giving the relationship between topological and piecewise linear manifolds. And the result is that in higher dimensions, dimension 5 and higher, it's almost true that every topological manifold can be triangulated, and uniquely so. There is one little Z obstruction in the fourth cohomology group with Z2 coefficients. If this obstruction vanishes, you can triangulate the manifold. And if a corresponding obstruction in the third cohomology group with Z2 coefficients vanishes, then the two triangulations are equivalent.
You mean triangulation or real triangulation?
By triangulation, I mean piecewise linear triangulation, yes. Though it is a very recent result that not every manifold can be triangulated as a simplicial complex. So that was an open question until about 6 or 8 months ago, and it's now been resolved. Okay, so these are very general results in high dimensions. They work basically in all dimensions at once. There is a 4 periodicity to the results depending on the type of homological pairings you have in the middle dimension. But I wanted to give you the 2 essential, to my mind, ingredients in the way you prove all these results. One is surgery theory. So suppose you're given a manifold and inside it you're given an embedded sphere. So here's a manifold, some high dimension, and here's an embedded sphere. And I'm going to suppose that this sphere has a trivial normal bundle. So there's a little tube around the sphere that looks like SK cross Bn minus K. So in this case, in this picture, this would be the D n minus K. And it's a nice product neighborhood. To do surgery is to cut out the interior of this neighborhood and sew in something else with the same boundary. And what the other object that you use with the same boundary is simply Sn minus K minus 1 cross D K plus 1. Maybe I could give you the simplest possible example of this when K is 0. So here's a manifold. Here's an embedded 0 sphere. It has always trivial normal bundle. So I cut these 2 balls out and I glue in an interval across the sphere of 1 lower dimension. So that's in fact the connected sum operation. So connected sum is the simplest, the first surgery you can do. You in fact can do surgeries in higher dimensions as long as you have spheres with trivial normal bundles. So that's the basic operation in surgery theory. And the other essential point in high dimensions, and this is where high dimensions are important, is the so-called Whitney trick. So suppose you have submanifolds of complementary dimension, X and Y, inside a smooth or P-all or even topological manifold. And suppose they're both of codimension at least or greater than 2. Then if M is simply connected, you can arrange that these submanifolds meet transversally. That you can always do. So when they cross, they'll cross in points where their tangent spaces are complementary subspaces. And then the Whitney trick allows you to get rid of extra points of intersection. So you can arrange that the number of points of intersection, the geometric intersection, is equal to the homological intersection number, its absolute value. So you can get rid of excess points of intersection. I think I have a picture here. Let's see. Yes. So here's the Whitney trick. I've imagined up here my surface X, my submanifold X, and here's my submanifold Y, and they're meeting in 2 points which cancel homologically. So this has maybe a positive intersection sign. This one has the opposite, negative intersection. So when I go to count the homological intersection of these manifolds, these 2 points will cancel. They don't contribute to the homological intersection. And the Whitney trick is to find an embedded disk, which I've drawn here, whose boundary is a union of 2 arcs, one on one of the submanifolds, the other on the other submanifold, and otherwise embedded and disjoint from the submanifolds. If you can find that, you simply push one of the submanifolds across the disk until it misses the other submanifold. And you remove in this way the 2 points of intersection. Okay. So in order to do this, you have to be able to find this disk. That's what's not given. You're given that x and y, the surfaces, you have these 2 points of intersection, and you can then draw arcs, but nobody guarantees there's a nice embedded disk like that. The Whitney trick is to find such a disk, at least in high dimensions. So the way you find this disk is, suppose you're working in a simply connected manifold, which we usually are in this talk, and these submanifolds are of codimension 2, more than 2. Since I'm in a simply connected manifold, this loop will bound a disk. By general position, I can make that disk embedded, and by general position, I can make it disjoint from the 2 surfaces. Then I have the Whitney disk, and I can remove the points of intersection. So for that, you need dimension at least 5, and that's why all of these general theorems that I've been talking about had the restriction n greater than or equal to 5, and most of them are not true or unknown in dimension 4 for exactly this reason. This is what fails. So I wanted to give you one sample result that indicates how you use surgery and the Whitney trick to, well, I'm going to sketch a proof that if you start with a manifold sigma 5, homotopy smooth and homotopy equivalent to the 5 sphere, in fact, it's diffeomorphic to the 5 sphere. So this is the smooth version of the Poincare conjecture in dimension 5. So first of all, you have to do a little homotopy theory, and you learn that this 5 manifold is the boundary of a compact 6 manifold, 6 should be up there, with trivial tangent bundle. Now you do surgery, as I indicated here, on, well, 0 spheres to make this 6 manifold connected, though of course you could just throw away the components you don't need. On circles to make it simply connected, and on 2 spheres to make H2 equal to 0. So now we have a 6 manifold whose boundary is this homotopy 5 sphere. It has no it's simply connected, it has no H1 and no H2. So by Poincare duality or Lefschetz's duality, all that's left is the third homology. That's a free abelian group. It has an intersection pairing on it, which is skew symmetric because I'm in dimension 6, and therefore it's a sum of, algebraically, of pairings like this, standard hyperbolic pairings. And that's a simple fact about skew symmetric pairings non-degenerate over the integers. All right, so that's what it looks like. Now we're going to embed a family of 3-dimensional spheres that exactly represent this basis, and I'm going to make their intersection in pairs 1 point. So suppose I had just a rank 2. I would choose 2 homology classes. I would represent them by spheres, which using the Whitney trick I can make embedded, and I can make those 2 spheres meet in exactly 1 point. Now I do surgery on one of those 2 spheres, and I produce, when I do that, I kill both the homology class of that sphere and the dual sphere, and so after I've done all this surgery, I end up with a manifold homotopy equivalent to the 6 ball. So on the way of trying to prove that this manifold sigma 5 is the 5 sphere, the first thing I prove is that it bounds a contractible 6 manifold. That's what I've just sketched here. Now you actually have to do these arguments again and prove that this 6 manifold is in fact the 6 disk. And it's very similar sorts of arguments, again using, well, Morse theory and handle moves, and then the Whitney trick once again to get rid of the last set of handles. So once you do that, it turns out that this manifold has a Morse function, which is, let's say, 0 on the boundary, has no critical points except for the maximum, and then that, by integrating a vector field, you prove it's the 6 ball. And if it's a 6 ball, its boundary is the 5 sphere. Okay. All right, well, that's a brief recap of what happens in 5 dimensions. This was all known by about 1975. So of course, attention immediately moved to the low dimensions. Well, in fact, dimension 3 had been a focus of attention from Poincaré's seminal work in 1900. I think the general feeling was, well, 1 is trivial, 2 is not so bad, 3 is so hard we can't understand it, so there's no hope in 4 or 5 or 6. And it was Smale's great insight that if you skip over 3 and 4, in fact the higher ones, because of the Whitney trick, are much easier to understand. And then out of that and some of Milner's work on surgery came this whole theory that proved everything that I was just describing. Okay, but that left 3 and 4. These techniques don't work in 3 and 4. As I say, much was known in 3. In 75 years, a lot had been proved in dimension 3, but a lot was not known, but there were at least conjectures, and as we'll see in the 70s and 80s, even more conjectures about what things should look like in dimension 3. Dimension 4 was wide open, totally unknown. I should say, by the way, I remember in those days having vigorous debates with Yao. I was saying, look, topology is this great subject, right? Look at what it's done in high dimensions. Great theorems. You don't have any theorems like that in algebraic geometry. We've got great theorems here. We're going to figure out the low dimensions. Yao said, no, you're going to need geometric techniques in the low dimensions. Well, I have to confess, Yao was right. Okay, 4-dimensional manifolds. So, again, as was pointed out earlier, in dimension 4, smooth and piecewise linear are the same. So if you have a piecewise linear 4 manifold, because of everything you know about 3-dimensional manifolds, in fact, you can give it a smooth structure. So there's no difference between those categories. But as we will see, there's a huge dichotomy between the topological category and the smooth or piecewise linear category. And this distinction is unlike anything that happens in any other dimension. Okay. Well, again, we want to study the same basic approach to 4 manifolds we took to higher dimensional manifolds. Start with an understanding of the homotopy theory and try to understand the relationship of try to understand all manifolds in a given homotopy type. Well, I'm going to stick to simply connected manifolds. They're hard enough. So the only invariant of a homotopy invariant of a simply connected 4 manifold resides in the second homology of the manifold, which is a free abelian group of finite rank, and it has an intersection form, which, unlike what I was doing in dimension 6, this time the intersection form is symmetric. So it's a symmetric unimodular form. That means it's represented by a symmetric integer matrix of determinant 1. Well, we basically understand all such symmetric intersection forms. They're determined by their rank, the rank of the lattice, the signature, which is something you get by extending scalars from Z to R and diagonalizing and counting the number of plus eigenvalues and number of plus signs down the diagonal minus the number of minus signs. And then there's one last integral piece of information, which is whether or not the form is even. You look at x dot x, that's an integer. If it's always an even number, the form is said to be even, otherwise it's odd. Okay, forms are completely classified by these 3 invariants, and they satisfy a couple of simple relationships, which I won't write down. That's true except for definite forms. So when the form is positive or negative definite, things are much more complicated. They're not completely understood. There are only finitely many up to isomorphism in each rank, but a complete list of them is not known. The first non-trivial one is the Cartan matrix of the exceptional Lie group E8. Has rank 8, signature 8 or minus 8, and is unimodular and even. And they just get more complicated from that. There's a beautiful one in dimension 24 called the Leach lattice, which is related to some of these exceptional finite simple groups. Okay. So that's the homotopy theory. The homotopy theory of simply connected 4 manifolds is the theory of these even intersection forms. It's theory of these unimodular intersection forms. Okay. So you immediately can ask, well, which forms are realized as forms on manifolds? Are they all realized? And how many different manifolds realize a given form? Well, before I get to those questions, I just want to point out that there are lots of very interesting form manifolds, topologically interesting, but also interesting for other more geometric applications. We have rich sources, complex algebraic surfaces, or complex surfaces more generally, and also symplectic manifolds, which is a generalization of complex algebraic surfaces. And of course, we can take those, we can take connected sums, we can do various geometric or topological operations on these manifolds. Well, we can ask, does this generate all the simply connected manifolds? What happens when we think about non-simply connected manifolds? These questions are wide open. Nobody knows.
You consider only eventable?
Yeah, for simplicity. Yeah. I mean, that's not essential, but let's consider orientable manifolds here. Okay. Well, those are some of the questions. Now let me talk about the techniques. And there's going to be, this part of the talk breaks into two. There are going to be the smooth techniques and the topological techniques. They're completely different, and the results are completely at odds. So the smooth techniques, well, the real breakthrough goes back to Donaldson in the early 80s, using ideas that originated, well, ideas that were in mathematics, but this use came from physics, the physics of gauge theories, which was describing the various forces and elementary particles. So you look at a principal SU2 bundle over your form manifold and the space of all connections on this principal bundle. Now there's a huge group, an infinite dimensional group of automorphisms, the automorphisms of the bundle P over the identity of the manifold M. That group naturally acts on the space of connections, and the quotient space, which you think of as, well, it's the gauge equivalence classes of connections, or the geometric information in a connection, is the real object of interest. The action of the group on the space of connections is going to be basically essentially free, except on the reducible connections where, if I'm doing SU2, the stabilizers are a circle. So you have a pretty good understanding of the space of all connections, its homotopy theory, and the quotient by the gauge group. So that's all just homotopy theory. The homotopy theory of this space, in fact, because it's infinite dimensional, the geometry, topology of this space is completely determined by the homotopy type of the form manifold and the principal bundle. We don't have any extra information at this point. But now put on a Riemannian metric. Once you do that, the two forms on the manifold decompose into the self-dual and anti-self-dual parts under the metric, and one can write down the anti-self-dual equation for the curvature of your connection. So A is the connection, FA is its curvature, and we write down the equation that the self-dual part of the curvature vanishes. And that turns out to be a nonlinear elliptic equation, at least elliptic modulo the action of this infinite dimensional group. And the formal dimension of the moduli space in the quotient space is given by this formula, 8 times the Chern class of the principal bundle minus a topological piece here from the manifold. And you can prove for a generic metric, this is a smooth manifold of this dimension, except possibly where it meets the reducible connections. And at where it meets the reducible connections, it's the quotient of the smooth manifold by a semi-free S1 action, and S1 action fixing only the central point. Okay. So let's take the special case when M is simply connected and negative definite. And the first Chern class of the bundle is 1. So in that case, we do this computation. The dimension of the moduli space is 5. Its singularities are isolated points. They come from reducible connections, and there's one of those for each solution in cohomology to the equation x squared equals -1 up to psi. So you count the solutions to this equation in cohomology up to psi, and there will be exactly one reducible connection, one singularity in the moduli space for each pair of those solutions. Okay? So that tells you the structure of the moduli space near its singular points. It looks like C3 mod the standard action of the circle. Cone on CP2 is the quotient. Now the moduli space turns out is non-compact. So it's a 5-dimensional object. It has these fairly simple singularities, but it's non-compact because the curvature of the connection can actually concentrate or bubble near a point, and it can bubble near any point in the manifold. So it turns out that it can bubble near any point and uniquely, so you get a neighborhood of infinity. The non-compact part of the moduli space is simply a copy of the manifold across a collar. So we get a 5-dimensional manifold whose one end is the original 4 manifold we started with, M, and then we have these singularities. Let's cut out neighborhoods of the singularities, so we'll get boundary components CP2, and we'll have the number of CP2s is given by the number of solutions up to psi of this equation. But the signature of the manifold M and the signature of this manifold have to be the same because there's a bordism between them. On the other hand, the signature of this manifold of CP2 is 1, so the signature of this thing is at most plus or minus k. It's somewhere between plus k and minus k. So this means that the number of pairs of solutions to x squared equals minus 1 inside this form is at least the signature of M. But now you go back and look at the forms. If you have that many plus or minus 1s, your form is diagonal over the integers plus minus 1. So this is Donaldson's first theorem. Well, here's a picture of the moduli space. So here's the non-compact part of the moduli space, which is the original 4 manifold. Then we have this moduli space about which we don't know too much, but it's a smooth 5 manifold. And then these cone-like singularities over the CP2s. So we cut out these neighborhoods. We got a bordism from the 4 manifold we started with to a collection of CP2s. And we concluded that the form, the intersection form of the manifold is diagonal. So this is Donaldson's first theorem. If you have a definite form that occurs as a form of a smooth manifold, say negative definite, then it's in fact the form of a connected sum of CP2s with the opposite orientation. None of these exotic forms, like E8 plus E8, can occur as an intersection form of the smooth manifold. So this is a partial answer to the question which forms can be realized. The answer is not all of them. And in particular, all but the trivial definite forms cannot be realized.
What does this mean?
Say again?
Yes. The previous slides don't seem to...
Simply connected.
Simply connected. Okay. Donaldson went on to study this moduli space and its effect on the topology. So let's consider manifolds that aren't negative definite. And again, the moduli space, as I said, the formula, well, we're going to take a simply connected manifold, so its first Betti number is 0. So the formula for the dimension of the moduli space is given here. And this is a submanifold inside the irreducible connections on the bundle mod the action of automorphisms. Now, you can calculate the cohomology of the space, and in fact, there's a natural slant product from the homology of the manifold into the cohomology of this space that shifts dimension from star to 4 minus star. This moduli space is essentially compact, so I can, and orientable, so I can integrate cohomology classes over the fundamental class of the manifold using this map from the homology of the manifold into the cohomology of the space of connections mod gauge, which is the space in which the moduli space sits. I can take products of these image cohomology classes of the correct dimension, integrate them over the fundamental class of the moduli space, and get what are called the Donaldson polynomial invariants from the symmetric symmetric algebra on the homology into the integers. And this turns out to be a very powerful invariant of four manifolds. You can prove many theorems with it. Let me just cite one. There are infinitely many non-diffeomorphic, simply connected algebraic surfaces, all homotopy equivalent to CP2 blown up at 9 points. Well, these surfaces were known for a long time, come from Kadira's classification of surfaces. For those of you who know something about the classification, they're elliptic surfaces, and these examples are the examples with two exceptional fibers. So they were known for a long time. Those examples were known for a long time. The fact that they were not in the same component of moduli was known, complex moduli was known. What wasn't known was whether or not they were diffeomorphic. And Donaldson's invariance can be used to show that no two of them are diffeomorphic. So this is at odds with what happens in higher dimensions, where if you have a compact topological manifold, it has at most finitely many distinct differentiable structures. Well, okay, we haven't quite got there. It turns out these manifolds are all homeomorphic. So in the end, we have infinitely many non-diffeomorphic manifolds, all, I've said here, homotopy equivalent to CP2, but in fact, we'll see in a few minutes, they're all homeomorphic to CP2, blown up at 9 points. All right. Well, this theory developed in quite a surprising direction. It turns out there's another gauge theory coming from physics, whose moduli space of classical solutions can also be used to give invariants of four manifolds. These are the Seiberg-Witten invariants. It turns out these invariants carry information, the same information that the Donaldson invariants carry, but they're technically easier to work with. So while they carry the same information, they were more useful for applications because you could see how to prove the theorems you wanted to prove, and I'll just give you one sample theorem of that. It's called the Thom conjecture. It goes back to a conjecture René Thom made in the 50s. A smooth algebraic curve of degree D in CP2 has minimal genus among all embedded smooth surfaces in its homology class. This was a famous question. Well, this is a sample of the results you can prove. There are many, many results along these lines using these invariants. And what they show you is that the classification of smooth four manifolds is much richer than the homotopy classification, say in the simply connected world, or classification of these quadratic forms. It's a very rich subject, but it's so rich we don't even have a guess as to what all four manifolds, even simply connected four manifolds, look like, or how you construct them, or how you tell them apart. We have this one class of invariants which has told us a lot that was unattainable before, but it's not clear it's gotten us any closer to understanding what they all look like. It's just convinced us that it's an extremely hard problem. So, to summarize, nice invariants show four manifolds are quite complicated. They lead to lots and lots of questions, and we don't even have conjectural answers. So four manifolds is still wide open in spite of this great advance that gauge theory had from the 80s on. Okay, so I finished the first part of my talk with what we know about the topology of smooth four manifolds. We have some nice new invariants, but we have more questions than answers, and for large parts of the theory, we don't even have any conjectures. So I want to turn now to the parallel story, the topological story in dimension 4. So let me just remind you of the Whitney disk idea. So let me concentrate and try to do the Whitney disk trick in dimension 4. So I have two-dimensional surfaces, say two spheres, in a simply connected four manifold, and they have some excess intersection. They have a pair of points I'd like to cancel because They're transverse points of intersection, but they count with opposite sign in the homological intersection. So what do I need to do? I need to do exactly what I was doing in higher dimensions. I have these two spheres. They have these points of intersection I want to cancel. I want to try to put in an embedded 2-disk that bounds this loop given by an arc on one 2-sphere and an arc on the other. And I need to make this disk embedded, and I need to make it disjoint except along the boundary from the two 2-spheres. Well, that's the same problem I'm trying to use the disk to solve. Because as I go to put this disk in, it will have self-intersections because it's a 2-dimensional surface in a 4-manifold, and it will meet excess intersections with each of the spheres. So I have the same problem to put in this disk is the same problem I'm trying to use the disk to solve. Well, we can do it again. So I have excess intersections of this disk with one of the spheres. I could try to put a Whitney disk in there. But again, it will have self-intersection and it will meet the spheres, and it goes on forever. Well, in fact, that was the starting point of Michael Friedman's attack on the topology of 4-manifolds. He built an infinite tower, starting with a problem where he wanted a Whitney disk. He put in a singular one that had excess intersection points and met itself, and then he put in possible Whitney disks for those with self-intersections, and he kept going. He built a tower, an infinite tower, doing this process over and over again. And then inside that tower, he was able to give a recursive argument to find a topological disk, which is incredibly non-smooth because it's given as the limit of an infinite process. And that was the Whitney disk. So in this manner, he was able to prove in the topological category the existence of Whitney disks in dimension 4. And once you have that, surgery theory works in dimension 4, at least for simply connected manifolds, and you get the analog of all the results in higher dimensions for topological 4-manifolds. Well, that's what I just said. Okay. And so here are 2 sample theorems that Friedman proved. Unlike the smooth classification where Donaldson showed certain forms don't exist, Friedman showed any form does exist for a topological 4-manifold. So any unimodular symmetric form is the intersection form of a simply connected 4-manifold. And up to topological equivalence is either the intersection form of 1 or 2 4-manifolds. And if it's the intersection form for 2, then only one of them can be smooth. In fact, only one of them can be smooth after you cross with a circle. So that's the classification, topological classification of simply connected 4-manifolds. It's a complete classification. Similar, using Whitney disks, he was able to show every homology class in CP2 is represented by a topologically embedded 2-sphere. So these results are at great variance with the smooth results that come out of Donaldson theory. And they have many striking consequences that make dimension 4 look like no other dimension. So as I've already, I said there are compact simply connected 4-manifolds with infinitely many differentiably distinct structures. If you have a compact manifold, it can have at most countably many different differential structures. But if you have a non-compact manifold, that's no longer true, and R4 has uncountably many distinct differential structures. So if you think about R4 as a topological manifold and you want to do calculus on that topological manifold, there are an uncountable number of ways to do calculus on that manifold. In every other dimension, the topological Rn has a unique smooth structure. There's a unique way to do calculus on Rn. Okay, so that finishes my summary of 4-manifolds. And what you should take away is that the theories are vastly different. Topological form manifolds look like higher dimensional manifolds. Surgery theory works at least for simply connected manifolds. And you can prove very, very strong classification results, find embedded surfaces that you want, and so on. The smooth theory, we have these nice invariants coming from physics, gauge theory, and they tell us that things are very rich and very different from the topology, but they're not strong enough, at least it doesn't seem like they're strong enough, to be the complete answer, the complete classification. So we need new invariants, or we need some construction technique to show that the existing invariants are powerful enough to distinguish. And it's wide open what the answer should look like. Okay, now I want to turn to three-dimensional manifolds. And our categories are all the same, dimension 3. So topological, triangulated, or smooth, doesn't matter. So we're going to work with smooth. Of course, for three manifolds, the fundamental group now becomes an essential ingredient in the story. For higher dimensional manifolds, I tended to focus on simply connected ones because they're much easier to deal with, and also because once you get to dimension 4, every finitely presented group is the fundamental group of some compact manifold, and finitely presented groups are not, can't be classified. So if you tried to classify all manifolds non-simply connected, you'd have trouble. Yeah. Okay, so that's one central feature. Another feature that's been clear from the beginning, that the fundamental group was an essential ingredient for three manifolds. It was much later in the story that it was realized homogeneous geometry was an essential central feature. And in fact, in the end, the classification is in terms of homogeneous geometries. So let me back up and talk for a moment about surfaces. So we know what all compact surfaces look like. They can all be uniformized. That is, they're either finitely covered by the two-sphere, by a two-torus, or they're hyperbolic, meaning they're the quotient of the upper half plane by a discrete subgroup of PSL2Z. I shouldn't say that, discrete subgroup of PSL2R, that you say, acting freely. So if I go to the universal covers, I have my possible universal covers are the two-sphere, the plane, Euclidean two-space, or the hyperbolic plane. And these all have homogeneous geometries. The plane is the flat, homogeneous geometry. Two-sphere is the round one. The hyperbolic space has its Poincare metric, and the group of isometries of the Poincare metric is PSL2R. So these are homogeneous geometries. If you look at the group of isometries of any one of these manifolds, it acts transitively on the manifold. So all points look the same. Now, homogeneous manifolds are always of the form G mod H, where G is some Lie group and H is a compact subgroup. And the way you see that is if you have a manifold M and G is its isometry group, it acts transitively. So you can identify the manifold with G modulo the stabilizer of a point. Since this is an isometry group, the stabilizer of a point will be a compact subgroup. So the manifold is identified through the action with a symmetric space. And then in fact the manifold is what's called a local symmetric space. It will be the quotient of this symmetric space by some discrete group acting on this side. Okay, so in the case of surfaces, S2 is SO3 mod SO2, R2 is the Euclidean group mod SO2, and the hyperbolic plane, I've already said, well, is PSL2R mod SO2. So we have those local symmetric spaces, we have those symmetric spaces, and then the compact manifolds that we would get would be by taking quotients of those, as I say, by a discrete group acting on the other side. We call these locally homogeneous manifolds. Manifolds whose universal cover is of this form, and the covering transformations are isometries acting on this side. And And so this theorem, the uniformization theorem, can be formulated to say every surface has a locally homogeneous metric. And the three possible types are round, flat, or negatively curved, constant negative curvature. If you go to dimension 3 and you ask, well, what are the homogeneous geometries that can possibly come into the picture? Well, to replace the 3 in dimension 2, we have 8. We have the 3 obvious analogs from dimension 2, the constant sectional curvature round, the 3 sphere, flat, R3, and hyperbolic 3 space. There's a hyperbolic space in every dimension. All right, well then we have the obvious products, S2 cross R and H2 cross R, so the homogeneous 2-dimensional geometry cross the homogeneous 1-dimensional geometry. How come I don't have flat cross R? That's because it's already here in R3. And then you have 3 twisted products. The universal cover of PSL2R, the nil group, upper triangular 3x3 matrices with 1s down the diagonal, and real entries. So it's a 3-dimensional Lie group. The nil group. And solve, 3-dimensional solvable group with normal subgroup R2 acted on by R star acting diagonally, hyperbolically. Okay, so that's it. Those are the only homogeneous geometries that are going to come up in this discussion. There are others, but they don't have interesting local homogeneous examples. All right. So we have 8 classes of locally homogeneous 3 manifolds that we would get by taking quotients of any of these 8 geometries by discrete groups of symmetries. So here we have the round 3 sphere and various finite quotients of it, Lin spaces, RP3, and so on. Here we have flat manifolds, tori and things finitely covered by tori. Here we get hyperbolic 3 manifolds, mainly compact or finite volume. These products give us, well, S2 cross S1 or a hyperbolic surface cross S1, and then these twisted products, the nil manifolds. You see from here, this group projects onto R2 with a central subgroup R, so your compact manifolds related to this group will project onto the 2 torus with circle as fibers. These are non-trivial circle bundles over the 2 torus. That's what the nil manifolds give. The solved manifolds give just the opposite. They give 2 torus bundles over the circle with a Nossoff monodrome. And then the PSL2, the universal cover of PSL2R gives us circle bundles over hyperbolic surfaces. So those are the kind of manifolds that will come up in these various homogeneous geometries. Maybe the first thing you would think of is, okay, maybe that's everything. But in fact, it's very easy to see that not every manifold in dimension 3 can possibly be locally homogeneous. The first example would be connected sum, which I've talked about before. If you take a connected sum of 2 manifolds, which I've drawn here, with one exception, RP3 connected sum, RP3, no non-trivial connected sum of closed manifolds can be given a locally homogeneous metric. And the reason is that this connecting 2 sphere, where we do the connected sum, will represent a non-trivial element in the second homotopy group. Well, the second homotopy group of the manifold and its universal cover are the same, so that would mean if this manifold were locally homogeneous, that pi 2 of G mod H would have to be non-trivial. You go through the list, the only homogeneous geometry with non-trivial pi 2 is S2 cross R, and so the connected sum would have to have an S2 cross R structure, and this one manifold that has such a structure, it's RP3 connected sum RP3, which is a quotient of S2 cross S1 by an involution. So if you take any pair of manifolds and do 3 manifolds and do a connected sum, you're not going to get a homogeneous 3-manifold. And there's one other example I want to give you, similar but made by using 2 tori instead of 2 spheres. So let's take 2 non-compact hyperbolic manifolds of finite volume, each with 1 end. We could do it more generally, but let's just stick to that case. So these, like hyperbolic surfaces, hyperbolic 3 manifolds of finite volume have cusps. Their ends are cusps. This time the cusps look like T2. The cross-section of the cusp is a T2 rather than a circle that is exponentially decaying as you go out to infinity. So here I have 2 hyperbolic manifolds with a cusp. Cut off the cusp and get a compact manifold with T2 boundary and simply glue the T2s together. This now makes a closed manifold constructed out of 2 hyperbolic pieces, and once again you can show that manifolds like that do not have homogeneous geometries. Their fundamental group is so big that the only possible homogeneous geometry would be hyperbolic geometry. On the other hand, this 2 torus injects into the fundamental group, and closed hyperbolic manifolds don't have Z cross Z's in their fundamental group, as you see by studying PSL2. So these manifolds also cannot be given a homogeneous geometry, locally homogeneous geometry. Okay. But the result, first conjectured by Thurston, the geometrization conjecture, is that any closed 3-manifold should be decomposed in 2 steps, and after the second step you end up with pieces that have homogeneous geometries of finite volume. And the 2 steps are of slightly different nature. The first is a connected sum decomposition. So if the manifold is a connected sum, you cut it open along a connected sum 2-sphere, you then get a manifold with 2-sphere boundary, and you fill in 3 balls to cap off the 2 spheres. That's called the connected sum decomposition. So you do that some finite number of times, and then you do a second cutting along 2 tori, in fact 2 tori whose fundamental groups inject into the manifold, and the result is a collection of pieces where you've cut along the 2 tori, you throw the 2 tori away, so you have open pieces. You might have some compact pieces also. But the conjecture, Thurston's geometrization conjecture, says that the result of this process gives you a collection of pieces, each of which has a, I should have said, locally homogeneous metric of finite volume. So it's in this sense that locally homogeneous geometry or homogeneous geometry accounts for all 3-dimensional manifolds. It's not that every 3-manifold has a homogeneous metric, it's rather you have to do this decomposition in order to find the geometric pieces. And I should say, maybe I have on the, well, I'll say it here. The connected sum decomposition is been known for a long time to be unique up to topological equivalence. So if you start with a 3-manifold, and you can break it along a finite number of 2 spheres, fill in the 3 balls, you'll get pieces which cannot be further decomposed. Those are called prime pieces. Every manifold has a prime every 3-manifold has a prime decomposition, and the prime factors, the pieces you get when you finish, are independent, except for order, of the way you did the decomposition. So the prime factor is unique. And these tori, this torus decomposition, if you choose it in such a way that the number of tori is minimal in the decomposition, those tori are unique up to isotope. So this decomposition is essentially a unique decomposition, it turns out. So this is Thurston's conjecture. Start with, so let's assume we've already done the 2-sphere cutting. Let's start with a prime 3-manifold. Then there's some finite graph, gamma, some finite graph. Some of the vertices of order 1 are marked with K for Klein-Bottle. Nothing else is marked. And there's a map from the 3-manifold, which is this prime 3-manifold, to the graph. It's transverse to the midpoints of the edges. So if you take the pre-image of the midpoint of the edge, it will be a surface with a nice product neighborhood in the three-manifold. So these pre-images, these surfaces, the pre-image of the midpoint of an edge is a torus, which we'll label by that edge. And these tori have fundamental groups that inject into the fundamental group of the manifold. That's a fairly technical condition, but it's absolutely essential because without it you lose all control. And the components of the complement, so where you cut open along the tori, there's one component for each vertex. So this map maps the components to the neighborhoods of the vertices and the tori to the midpoints of the edges. The components corresponding to a vertex with this K on them are twisted interval bundles over the Klein bottle. Every other component has a locally homogeneous metric of finite volume based on one of the 8 geometries. Now you might think it's a little funny that I had to have these exceptions here, the Klein bottle, but in fact what you say is you don't cut along 2 tori, you cut along 2 tori and Klein bottles. So instead of cutting along the torus that separates off this twisted eye bundle in the Klein bottle, simply cut along the Klein bottle. It's a little harder to think about because it's got a twisted neighborhood. But nevertheless, if you cut along tori and Klein bottles, then every piece you get has a locally homogeneous metric of finite volume. Okay. So I tried to draw a couple of simple pictures of what this conjecture is saying. So maybe the simplest non-trivial case would be where the graph is an interval. So we have one edge, one torus, here's the 2 torus, and it cuts the manifold into 2 pieces, one associated with this vertex, one associated with that vertex, and these pieces each have locally homogeneous geometries. I'm imagining here that each piece is hyperbolic, but they could be of other types as well. So this is the manifold that I constructed for you a few minutes ago. It doesn't have a locally homogeneous geometry, but it comes about from local homogeneous geometries by this construction over the graph. Just one other slightly more complicated picture. I can imagine the graph being with 4 vertices, 1 of order 3 and 3 of order 1, and this one has a K on it. So this piece is a twisted eye bundle over the Klein bottle. Maybe this piece is hyperbolic, maybe this piece is hyperbolic, and this piece in the middle is maybe a circle bundle over a should be a 3 times punctured surface, hyperbolic surface. So that would be a typical example. So here's a twisted Klein bottle. This is a hyperbolic piece, this is a hyperbolic piece. It turns out this is a universal cover of PSL2R piece. Okay. And you can imagine arbitrarily complicated finite graphs. So any finite graph, any decomposition with a homogeneous thing at each vertex with the right number of ends glued together arbitrarily will occur. That's what 3 manifolds look like. That's the geometrization conjecture. Okay, and now it's a theorem. As I say, it's funny to come to St. Petersburg to talk about this theorem, but nevertheless, here we are. Perlman, using a geometric technique, partial differential geometric technique that goes back to Hamilton called Ricci flow, proved the geometrization conjecture. So let me just say a few words about Ricci flow, and then I'll try to sketch at least the quality of the argument or the quality of the results. So again, we're imagining imposing, as we did in Donaldson theory, imposing a Riemannian metric on this 3 manifold. Well, I've already told you the 3 manifold is smooth. Might as well assume it's smooth. So it has a Riemannian metric. Of course, it has an infinite dimensional family of Riemannian metrics. And it's not clear that it has a good one. In some sense, we're looking for a good one, or at least on pieces, a good one. All right, well, this is an equation introduced by Hamilton, and also by the physicist, by the way, Dan Froudan. You look for a partial differential equation to tell a parabolic type equation that will tell you how the metric evolves in time. So you're going to now imagine starting with an initial metric and deforming it in time, called t, through this differential equation, and we deform the metric so that its time derivative is minus twice the Ricci curvature of the metric. Well, this is essentially a parabolic equation. In other words, its right side is an elliptic operator on the metric. But as in gauge theory, there is a proviso there. You have to work modulo the infinite dimensional group of diffeomorphisms. This equation has an invariance, the group of diffeomorphisms. It's a geometric equation. And it's only modulo the group of diffeomorphisms that becomes a parabolic equation. But you can work modulo the diffeomorphisms. Hamilton had a more complicated argument that didn't make use of slices or to this action. But anyway, he was able to prove short time existence and uniqueness of solutions to this equation when the manifold, the underlying manifold is compact and the metric is smooth. So if you start with a smooth metric on a compact manifold, you can solve this equation. You can solve this equation for some positive amount of time. And the solution is unique. If you have two different solutions, one will be a sub-solution of the other. Or said another way, if you take a maximal solution that exists for as long as possible, then all other solutions are sub-solutions of that one. Unfortunately, or actually fortunately, there are in this equation finite time singularities. So this equation does not exist long-term all the way to infinity. You will encounter finite time singularities, and you can't even estimate, well, you can't even bound how long before the first singularity. There are examples where the first singularity is arbitrarily close to your starting point. Nevertheless, Perlman was able to give a qualitative description of what these singularities look like in dimension 3. And in fact, he established some geometric control in the regions near where the singularities are developing. Turns out, it was known beforehand, maybe it's due to Hamilton, yeah, I guess it is, that singularities are only developing where in regions where the curvature is going off to plus infinity. So the scalar curvature is going off to plus infinity, at least in dimension 3. So here are what the three-dimensional singularities look like. For some strange reason, time is going down in this picture. I apologize for that. So stand on your hand to look at these pictures. So there are three basic types of degeneration singularity development in dimension 3. Let me start with the one, Let me start with the one down here. These are components that completely shrink to a point in finite time. So I've imagined a three-sphere, but it could be anything else that has a round metric. So the metric may not be round to begin with, but if it's sufficiently positively curved, it will shrink in finite time to a point, and as it shrinks to a point, if you rescale it up so that its diameter is 1, so you can look at it, the metric is becoming rounder and rounder. So these manifolds have round metrics, which in some sense you can see through the limit of these flows with an appropriate rescaling, but the flow becomes singular to finite time. If you started with a round three-sphere or any other round manifold, you can actually write down the solution to the equation, and it's just a conformal shrinking. The manifold stays round and shrinks down to a point, and you can even say when it does shrink to a point. So we see positive curvature, positive three-dimensional curvature leading to complete collapse in finite time. The other two related to positive two-dimensional curvature along a positive along a two-sphere. So they're called a neck pinch and a degenerate neck pinch. Now, I've sort of imagined there's only one singularity here happening in the middle. It could be more complicated than that. But nevertheless, the region where this singularity is occurring is a region that looks like S2 cross an interval, where the curvature of the S2 is becoming very positive and the S2 is shrinking then to a point. So that's called a neck pinch. It can be degenerate, maybe one side in fact is a 3-ball and this whole side collapses. It's called the degenerate neck pinch. So this is, grosso modo, Perlman's classification or qualitative understanding of what not so much what the singularities themselves look like, but what the regions of the 3-manifold where the singularity is developing look like. So this allowed him to do surgery, produce a new compact smooth manifold, and then restart the Ricci flow again, using that as initial conditions. And the way you do that is you cut away the singular regions that are contained in necks or degenerate necks. So if you had a neck pinch here, you'd simply cut there and cut here, and you'd have 2 bounding 2 spheres that you could cap off with 3 balls. If you had a degenerate neck pinch, you would simply cut it right here and replace this singular object by a nice smooth 3-ball. So that's what you do in the neck pinch and the degenerate neck pinch. For these round components, well, you can just throw them away. You already understand them. You don't need to worry about pushing them forward in any way. So you simply remove these round components shrinking to points. After you do that surgery, which you do at the singular time, you have a new smooth manifold, which in these regions where you've done your cutting and pasting is new and different, but everywhere else is just the limit of the Riemannian metric coming from below. So you have a new compact 3-manifold. You use that as the initial conditions to restart the Ricci flow. You go until you hit the next singularity, you do it again, you keep doing it. You go all the way to infinity, and you produce what's called a Ricci flow with surgery, defined all the way to plus infinity. Now, until recently, it was thought that this process might encounter infinitely many surgeries, though Perlman was able to show the set of the surgery times were discrete. But just recently, Richard Baumler has shown, in fact, there are only finitely many surgeries. So that's a nice technical simplification. Okay, well, what is happening topologically when we do these surgeries? Let's just go back. If we do a surgery in a neck pinch, we're doing the connected sum decomposition. If we do surgery in a degenerate neck pinch, we're just taking what was a ball before and replacing it with another ball. So topologically, we're doing nothing. And here, we're throwing away components that we understand, components with round metrics. So this operation is either completely harmless topologically, doesn't do anything topologically, though it does something geometric, throws away a pieceful component we understand, or does a connected sum decomposition. That's what the surgeries do in Ricci flow. So they do the connected sum decomposition and they remove components that have metrics of a constant positive curvature. Okay. Next thing you have to do is understand, now that you have a flow going all the way to infinity, what you hope, of course, is that it's an infinity that you see the nice structure you're looking for. And indeed, that's what Perlman was able to analyze. As you go toward infinity, the manifold divides into 2 types of pieces. There are pieces where the volume appropriately rescaled, and this turns out to be the appropriate rescaling factor, time to the -3/2, where that volume does not collapse. So this piece of the manifold is staying, and then there are regions where the volume rescaled by this does collapse. These non-collapsing regions, Perlman was able to show, converge geometrically to complete hyperbolic manifolds of finite volume. So suddenly we're seeing one of the pieces in the geometric decomposition, or one of the types of pieces in the geometric decomposition. We're finding the hyperbolic pieces. They will be complete but a finite volume. They can be compact as well. And they're arising as limits of the Ricci flow as we go to infinity. So the Ricci flow is actually producing the metrics that we're looking for on those pieces. Okay? The rest of the manifold, as I said, is collapsing. Well, so we find these hyperbolic pieces, we find they're two two tori as their boundary components. That we understand and we're happy with. Now we have to worry about the rest of the manifold, the part of the manifold that's collapsed. Well, collapsed regions, here the study becomes more topological or metric, but not smooth, not Riemannian metric. And the basic idea is that these collapsed regions, where the volume is collapsing, are in fact close in an appropriate sense to lower dimensional spaces with curvature bounded below, the so-called Alexandrov spaces. And the theory of Alexandrov spaces can be used to understand the topology of these regions. So the nature of the argument has changed now. Up until now, we've been studying this geometric equation, and we've been making analytic estimates, and we find these nice hyperbolic pieces, and we find some volume collapse. Now we move to topology. The flow, at least as it's understood right now, doesn't help us to find the other geometric structures. We have to use topology now. But fortunately, these topological pieces are well understood. And through this idea of lower dimensional Alexandrov spaces and limits, we can understand the topology of the collapsed regions. So, let me say a few words about Gromov-Hausdorff convergence and a little bit about Alexandrov spaces, and then I'll circle back to how you learn about the three manifold. So let's look at two compact metric spaces, X and Y. We say they're within epsilon of each other in the Gromov-Hausdorff distance if we can take their disjoint union and put a metric on that, extending the metrics on X and Y, so that X is within an epsilon neighborhood of Y and Y is within an epsilon neighborhood of X. Okay, if they're close as metric spaces. Okay, that turns out to be a metric on the space of compact metric spaces. And the first thing you have to prove is a nice elementary exercise. If the Gromov-Hausdorff distance between two compact metric spaces is 0, then they're isometric. That isn't quite evident from the definition, because it just, definition says the distance is 0 if for every epsilon you can find a metric on the disjoint union where each is within epsilon of the other. And you have to prove they're the same, they're isometric. Anyway, it's true. And then we say a sequence of, based metric spaces no longer have to be compact, converges in the Gromov-Hausdorff sense to another based metric space if the balls, for technical reasons you have to change the radius a little bit. If the balls in the sequence, there should be an n there, converge in the Gromov-Hausdorff sense, you take the epsilon n going to 0, to the corresponding ball in the quotient. That's true for every R. So that's Gromov-Hausdorff convergence. Now we're going to be applying this to Alexandrov spaces, which in particular are metric spaces and they're length spaces. Between any 2 points, there is an isometric embedding of the interval. That's length spaces. Now, the Alexandrov condition has to do with angles and the relation of angles and curvature. So, suppose we're given 3 points in our metric space, what's going to be an Alexandrov space, x, y, and z. Take the surface of the same constant curvature as you're talking about here, and in that surface find 3 points that have exactly the same pairwise distances as these. So distance from x to y is the same as distance from x tilde to y tilde, and so on. Then you can take the triangle in that standard surface, the hyperbolic surface, say, and you say the angle of that triangle at y is the comparison angle of x, y, and z in our more abstract metric space. It's the angle of x, y, z, the comparison angle of x, y, z. So I'm not trying to directly define angles in this Alexandrov space. I'm saying, in this space, I'm saying take the distances, move over to a standard hyperbolic space, construct the triangle there and measure the angle and call that the comparison angle. And then this space is an Alexandrov space with curvature bounded below by K, means that anytime you have a central point and three others in what's going to be the Alexandrov space, and you take the sum of the three comparison angles, you get at most 2 pi. So I'm going to just draw a picture to help you there. So you have the central point P, and then you have three others, A, B, and C, and we take these three comparison angles. And if they add up to no more than 2 pi, every time I have 4 such points, we say this is an Alexandrov space of curvature greater than or equal to K. There's a beautiful theorem in Riemannian geometry due to Toponogov, which says that if you have a Riemannian manifold of curvature, of sectional curvature bounded below by K, it is an Alexandrov space of curvature bounded below by K. So there's a relationship between sectional curvature and this notion of curvature when the manifold is a Riemannian manifold. So in some sense, this is extended notion of curvature to these much more general metric spaces, but we don't actually have a curvature, we just have what the lower bound for the curvature is. Now, the theory of Alexandrov spaces has been quite a bit developed. In particular, an Alexandrov space has a tangent cone at every point. And one way to get the tangent cone is to take, well, the definition of the tangent cone is you take scalings of the based Alexandrov space where the scalings converge to infinity, and the scalings go to infinity, and then that collection of base metric spaces converges in the Gromov-Hausdorff sense to the tangent cone. Just like a smooth manifold, when you scale it up, converges to its tangent plane. So an Alexandrov space has a dimension, which in the first instance is simply its Hausdorff dimension, but it turns out that that dimension is an integer, and in fact there's an open dense set inside the Alexandrov space that's a manifold of that dimension. This is, I'm doing a finite dimensional case here. Okay? And then there's a theorem that's very important in this study. It also explains why Alexandrov spaces would come into these sort of pictures. If you have a sequence of complete Riemannian manifolds of some fixed dimension, curvature, sectional curvature greater than or equal to K, then passing to a subsequence, there's a Gromov-Hausdorff limit, and this limit is automatically an Alexandrov space of dimension no bigger than what you started with, and curvature at the same lower bound. So if you take sequences of manifolds like this with curvature bounded below, the limit in this metric sense may not be a manifold, but it is an Alexandrov space, but it may not have the same dimension, it may have a lower dimension. If the volumes of the manifold in the sequence, or even the local volumes, are tending to 0, then the limit's going to be actually lower dimensional, strictly lower dimensional. So in the collapsing, now we go back to our Ricci flow and we apply this to the collapsing regions. So in a region that's collapsing, we rescale by what's called the negative curvature scale. So we expand out to as much as we can, so that after rescaling we have a ball of radius 1 with sectional curvature bounded below by -1. So that gives us a scale at every point, which depends on the curvature. And then we take any sequence of these balls, we'll have a Gromov-Hausdorff limit, which if the times are going to infinity, since we're in the collapsing regions, the volumes are going to 0, so the Gromov-Hausdorff limit will be an Alexandrov ball of dimension either 1 or 2. Well, Alexandrov spaces of dimension 1 are very easy to understand, they're intervals. Alexandrov spaces of dimension 2 are not much harder to understand. Topologically, they're surfaces. They have a finite number of cone points where the cone angle is some fixed amount away from 2 pi, and elsewhere they're nice topological manifolds. Anyway, they're pretty well understood. So that's what I just said. It's a manifold away from a finite number of cone-like singularities. If you look at the balls in the collapsing Ricci flow that are converging to such a cone-like singularity, those balls will be fibered by circles over this Alexandrov base. You'll have exceptional fibers or ciphered fibers over the cone points, and everywhere else it'll look like a nice smooth circle fibration. So this is prototypical of what happens. You understand something about the Alexandrov limit, this two-dimensional limit, and then you conclude something about the balls in the three-manifold. Likewise, when the Alexandrov space limit is one-dimensional, it's an interval, and the three-manifold, these balls in the Ricci flow, fibers over that interval or circle with fiber which is either a two-torus or a two-sphere. So these regions that you get from the Alexandrov space theory are completely understood topologically, and from this information together with how they're patched together, which also comes out of the Alexandrov space theory, you can completely classify topologically what the collapsed regions look like, and it turns out they're well-known topological manifolds, and they can all be decomposed along tori into pieces with homogeneous geometries. So, in fact, you get the geometrization conjecture. I just want to point out that Ricci flow does exactly what you have to do for the geometrization conjecture. The finite time singularities do the connected sum decomposition, which is absolutely necessary. And at infinity, you see at least part of the torus decomposition, the tori that separate the hyperbolic pieces from everything else. You have to put in a few more tori by hand. And as I said, the collapsed part and the tori dividing the collapsed part into its geometric pieces is not produced by Ricci flow, at least not right now. You have to use a priori topological knowledge, which is fairly elementary, has been known for a long time. Well, I make it sound like this is the end of the story. Three manifolds are completely known, there's nothing left to do. In fact, there's a lot of interesting questions. I haven't talked at all about invariants of three manifolds, but they're many, and they have complicated relations between each other. They're invariants coming from combinatorics, originally the definition of the Jones polynomial and its various algebraic generalizations to two and three variable polynomials, Kavanagh homology. Some of the invariants come from physics. Witten generalized the Jones polynomial from knots in the three-sphere to arbitrary knots and arbitrary three manifolds. They're the three-dimensional analogs of the gauge theories that prove so powerful in dimension 4, anti-self-dual and Seiberg-Witten Floor homology, and then some Heegard Floor homology, which is closely related to these, that comes from topology. So we have this plethora of invariants, but the relation of these invariants to the geometric classification is completely mysterious. For example, if you assume your underlying three manifold is hyperbolic, what can you say about these invariants? Do you know anything? Totally open. So there's a lot still to do to relate these invariants to each other, to relate them to topological constructions you might do, surgeries on knots and links inside the three manifold, and also understand how they're related to the geometrization. All right, well with that, I will stop. Thank you.
Thank you very much. Any questions?
Just my question about geometrization and vector is scale. Assume we have a closed, maybe arrangable three manifolds, which means a metric of strictly negative curvature, maybe a variable coefficient. And you apply Ricci flow to this metric. My question is, does it occur singularity after scaling on this metric?
So if you start close enough to a hyperbolic metric, the answer is no, there'll be no singularity development. In general, just assuming negative curvature.
Variable, it's part of case of Cannon conjecture.
Right. I mean, that manifold is hyperbolic, but
it's after all
it's hyperbolic.
Yeah,
but whether or not Ricci flow develops singularity, I think I only know that if you start close enough to hyperbolic.
Other questions? Actually, I have one. It's about, for the first part of the talk, how can one think about exotic R4? One hasn't any idea how to think about that.
No, I have no idea how to think about these incredibly crinkled handles that Friedman constructed. There's no picture. I mean, it's some infinite, elaborate, more and more elaborate, infinite process that you prove by theorems and points that topology produces a manifold. So from my perspective, the craziness of dimension 4 is that spaces that have no right to be manifolds, just in dimension 4 for some exotic reason, turn out to be manifolds. So they're too weird, they should never be manifolds, but they are. I mean, they're obtained by taking something nice like Euclidean space and doing a terrible collapsing of various pieces all over the place. And if you did this in other dimensions, you don't get a manifold, but in dimension 4, by magic, you get a manifold. But how to think about them? Verbitsky was asking me, what's the moduli space look like? I don't know. I mean, there are these one-parameter families, but I mean, maybe somebody knows more about the moduli space of those than I do. I don't know much about it, but is it Hausdorff? Is it finite dimensional? Do those questions even make sense?
Any other questions? Okay, please.
What do you think about Matveyev's spines as a powerful invariant of three manifolds?
I'm sorry, do I think of it?
Well, what do you think of it? You listed some invariants, but you know that Matveyev's spines is the complete invariant. So it's very powerful.
But
and it's calculable. So why don't you list it by computer?
I don't think I want to touch that.
Okay.
Okay, if there is no questions, let's thank John Morgan for a very beautiful lecture.